let's make a start for this DNS and Dnssec session. I don't need to introduce myself. Just we need a core speaker. First up, where's the list? I should have somewhere here. No, it's not the thing. So first up, Eddie from ISC. Now floor is yours. You have 30 minutes, including Q&As.
Okay. All right. Thank you very much. So, hello, I'm Eddie Winstead. I work for ISC. How many of you run Bind by chance? A few. Very good. Thank you for doing that. So today's topic, I'm going to be talking about DNS firewalling, otherwise known as RP. I'm in Asia Pacific, so RPZ. Right, response policy zones. So this is what we're going to do. Let's do that. All right, so when we talk about DNS response policy zones, I want to make clear that what we're talking about doing is making a change to the DNS mechanism at the resolver level. So if you think about the DNS ecosystem, if you will, there are clients that ask questions, and then there are resolvers that go out and ask authoritative servers on questions on behalf of those clients to get the answer back to the client. So when we talk about response policy zones or DNS firewalls, we're making a change at the resolver level. Okay. So in today's internet, we have this situation. How many of you have been doing internet things long enough that you used to operate services where people didn't send you malicious traffic? I'm old. Yeah, okay. All right. In today's internet, obviously, there are lots and lots of malicious parties trying to do lots and lots of things that it turns out it's very handy for them to use the DNS for. Okay. So some of them we have listed here. So botnet CNCs, of course, we want to, in terms of if our clients have been owned, so to speak, and they're part of this botnet, usually they have to do some DNS requests and some traffic to, connect back into their commander or whatever. So we're talking about here trying to prevent that connection from happening. So it prevents further damage from occurring. And also can give you some information on which of your clients maybe are having a problem. And then malware, of course, we're trying to prevent any new infections. And we all get these emails that promise us great things, right? If we just click here, yeah, all right. So it turns out that click here usually involves the DNS lookup. So if I'm a client and I am, I know not to click things usually, but a lot of people, it turns out on the internet, just click away. So if I'm a client and I click on that link, if my resolver is doing DNS firewalling, it will prevent me from going on to that malicious site. Okay. And then the other part of this is, the whole point of providing resolver services is so your clients can have their questions answered. So you want to free up and maintain your resources for the legitimate queries. So these days, there are a lot of options for resolver services. Of course, who in here uses 8.8.8.8? From time to time. I do from time to time, yeah. Depends on where I land and what people might be doing to the DNS where I am. There's also quad9.net. This is a new one that was announced back in November, so similar thing. So those are, of course, free to use, quote unquote. I have a friend that often says, if a service is free, then you are the product. So that's something to keep in mind, right? OpenDNS these days was bought by Cisco, and then Nominum as well has a product. Nominum was recently purchased by Akamai. So these are some of the options that you can do if you don't have in-house capability to provide resolver services to your clients. Now, there are a lot of reasons that you would want to do this yourself, and a lot of organizations still do provide their own DNS resolution. Typically, if you're an ISP, You know, I've actually seen some ISPs in the world that tell their users that for DNS, use 8.8.8.8 and 8.8.4.4. Okay, if I was a customer of that ISP, I would be a little concerned that they either don't care enough or they're not knowledgeable enough to run their own DNS, right? So there's reasons that you want to do these your own in-house. If you're using the appliance type vendors, the OpenDNS or Nominum, those can certainly come with a certain higher cost. So if you run your own in-house resolvers, you can have a lower cost. So one of the key selling points, though, on the appliance side for providing recursive services is that they'll do this DNS filtering for you, DNS firewalling for you. So what we're talking about today is sort of an open source way to do this yourself if you want to. So if you still maintain your DNS resolutions, resolver services yourself, this is a way that you can do this with open source. I also want to point out that even though I do work for ISC, we developed, DNS RPZ was actually invented at ISC, but we developed it as an open standard. So it's implemented by many different vendors. All right. So well, how many DNS admins do I have in here? How many of you do DNS stuff? Okay, good. So for those of you that do, you're very likely familiar with the concept of a zone transfer. Yes? Okay. For those of you that do not, and there are actually quite a few that don't do DNS, zone transfer is a mechanism among usually authoritative servers for getting data from one server to another server. So if I am an authoritative server for isc.org and I want to provide my data to our moderator, he would perform a zone transfer of my data, and then he would be authoritative for isc.org as well. Okay? So it turns out with response policy zones, we're making use of this already baked in zone transfer piece of the DNS protocol. So if you've been doing DNS things for a while, then implementing RPZ is really, of course this is coming from the DNS guy, right? It's really pretty simple, right? But it is. If you've been doing DNS for any time at all, you already know how to set up zone transfers. So you can set up RPZ. So what is packaged really is this zone data that says essentially if there is an answer of this value, then I want to replace that answer with one that I'm going to provide. Okay. All right. As I pointed out earlier, there are lots of implementations of RPZ. These are some of them. They're all in alphabetical order except for open source. So I thought we'd put ourselves last. So, but you can run RPZ on any of these implementations. So this is what it looks like within a bind server specifically. So your client request comes in, and note that I don't have a pointer, so I'll do it myself. Note that the recursion and or lookup within cache still occurs. Okay, so this isn't something that says if I get this query, I'm going to immediately give them a different response. We're going to go do the work, because in a lot of these rules that we're going to set up, we need to know what the answer is. What we're really looking for is the answer a known malicious answer, right? So we go out and do all that work. Once we get that response, then we can take a look in our RPZ zones, see if there's any matches. If there's no matches, of course, we just pass on the normal regular DNS answer. If we do get a match in our RPZ zones, then we can do some different things with that answer. So some of the most common ones are you can pass it through. The reasons that you would want to pass through, we'll talk about some of them coming up. Very common one is that you just send back index domain. So if the client asks a question, it produces a malicious answer. The client never receives the answer. They receive a response that says that what you asked for does not exist. Similarly, you can also provide no data, which means the answer, what you queried for exists, but there's no record of that type. Okay. Another common one is that you would provide some local data. So we'll get into it a bit here in a second. But if you have a malicious response that's known, then maybe you want to send that client to sort of a walled garden environment. So you send them to a website that says, hey, please contact us so we can take a look at your computer. All right, so this is some of the stuff that I was just talking about. What I didn't talk about, though, was what we trigger on. So there are lots of options. You can, of course, you could trigger on what the actual query is, the queue name. You can query on actually the client IP. If I have a known set of client IPs that I might want to provide some different answers to for some reason, then I can use RPZ for that. RPZ, sorry. IP that's in the response, if I have a known IP address that is malicious and that is coming back in the answer, then I can trigger on that and provide a different response to my client. Same thing with, very commonly, the malicious parties make use of the same name servers. They have the same authoritative name servers. So if in the answer the authoritative data comes back with a name server, then I can trigger on that and do something with that response as well. And again, these are the ones I just ran through, NX domain, no data. These are the options that I have to send back to my clients. All right, so here's a pretty simple example of and a common one, a walled garden environment. So if I have a setup, those of you that do DNS on a daily basis know about $origin. This is usually what you find in a zone file. Yeah. For those of you who don't, you just have to trust us. Okay. But essentially what I'm saying here is if this known name server comes back in a response in the authoritative data, then I'm not going to send that response to this client. What I'm going to send them is something that I have set up here next. So if this query came in, and it matched in the authoritative data of this name server, then what I'm going to do is send them back this answer. I send back the CNAME, and then this A record, which is local to me. And then local to me, I have already set up this zone, and then I'm running a web server on this that says, hey, your PC looks to be having some troubles. Please contact support, blah, blah, blah. Yeah? All right. So one fun thing that we've done over the last, I think this was about 16 months ago now, Rackspace. Have any of you heard of Rackspace? Yeah, okay. So Rackspace in the US is one of the very large cloud providers. Okay, so they do hosted services, blah, blah, blah. They are a direct support customer of ISC, so we got to work really closely with them when they deployed RPZ. So we're going to talk about that a little bit and the results they saw. So so obviously when you do hosted services or cloud services, a lot of that is based on providing DNS for your clients, right? So Rackspace knew that they had lots and lots of malicious DNS traffic going on. They just didn't know what could we do about it, right? So they started looking at RPZ. In October 2016 is when we actually went through with them and implemented RPZ. So this is, everyone loves the great graph. How many managers do I have? Just a few? Okay. Managers always like graphs, right? That's the joke, yeah? So, hello, Jeff. So they knew they had this traffic, obviously, so they were graphing this known malicious traffic, and they implemented RPZ at that point. And, this is typically what you want to see in a graph when you do an implementation like this. Now, what would be nice to see as well is that, it would be nice to have a graph that shows legitimate traffic, because that's certainly not what we want to see. That's not the graph we want to see if we're doing legitimate traffic, right? All right. So, this is their results. I will say how they got to this. This is a really good graph and a really good picture, but how we got to this point was more complicated. Okay, they have. I don't know if I can give you exact numbers. They do a lot of DNS queries. Okay, and they have a lot of authoritative zones as well. So they actually, one thing we love about them as a customer is that they really push the envelope on what our software can do. So in this case, RPZ there were some performance problems that we worked out with them before they actually did the real implementation. So. All right, so in the Rackspace case, now I should say that typically when you implement RPZ, there are two options that you can do. You can do local, your own defined response policy zones. You can also subscribe to feeds. All right, do I have any security people in the room? People that only focus on security? Only, okay. I hate to say it, but you guys are typically kind of odd, right? So, no offense. But if that's not your specific focus, then you want to rely on parties that is their specific focus. So there are several of these, and ISC is we don't have any we don't sell feeds, and we don't have any preferred feeds. In the slides, I will list all the available feeds. But know that in the Rackspace case, they chose in their own procurement process, they chose to use Spamhaus. Okay, so this is a list of I think 5 of the named feeds that Spamhaus uses. So this is what they saw almost immediately, and I should note the next couple of graphs sort of cover that 48-hour period that we saw in the prior graph. Okay. So lots and lots of hits, of course. Now, so this slide kind of points out that it's not exactly all about your number of hits, right? Some of this is, if it's very malicious traffic, it doesn't matter if you only had 3 hits. It's really nice that you were able to drop that. Okay. And then again, this is over that 48-hour period. What they saw blocked, 217,000 and some domains. They actually had 275 million hits, and estimated 8734 devices that were actually protected by implementing RPZ. All right. So this is what they were able to do. One of the key things is, again, if you see clients that are being hit by this, or their queries are being rewritten, or their answers are being rewritten and given a different answer, then you know something is probably amiss with that client. So they're able to be proactive about informing their clients. A lot of these, you saw a bunch of traffic there for the, some of this actually lowered their customers' bills because the traffic levels went down. So lots of good things. All right. So again, I've mentioned that all this RPZ is available in many different forms of open source and commercial products. I'm a bind guy, so I'm going to show you how to do this in bind, but just know that you can do this in lots of other software as well. If I tried to do the other software, you probably wouldn't have a successful deployment. Okay. So we're going to look at specifically in the Spamhaus example. So one of the things that I haven't said yet, but I usually say a lot, is when you're going to do something like this, make sure you do logging, and do logging first. Okay, so there's a way that you can configure this to just enable logging, so you can see what would be dropped, what client or what answers would be changed and sent back to the client. Okay, highly recommend you do that before actually the real deployment. I'll show you how to create a local RPZ zone, and then how to do this as master and slave zones, again making use of standard zone transfer, and then how you actually enabled RPZ. All right, so if you run bind, then you're very familiar, hopefully, with how to do logging. So here we are essentially establishing a channel called RPZ log, RPZ log. And then we are sending category RPZ to that log. We are rotating the log as based on file size. Okay. So again, RPZ it's a little bit I want to say new, but it's actually been around since 2010. But it makes use of all the things that you're already familiar with, both in DNS protocol and in name server configuration. So this may be a little bit tricky to read from the back, but this is essentially establishing our local zone file. So here we have rpz.local. In this case, I'm going to do some whitelisting based on, if ISC ever gets identified as sending malicious traffic, certainly I don't want to rewrite my own responses, right? So I'm whitelisting my stuff. In this case, these are the spam house name servers, so I'm whitelisting them as well. And then here I'm doing baddomain.com, and so I'm going to CNAME anything that comes in for baddomain.com, and also wildcard anything within baddomain.com. So what this will do is if queries come in for baddomain.com, my resolver goes out and does the work. It says, oh, we're sending them to baddomain.com. Then we're going to rewrite that answer and say, NX domain or whatever we choose. Okay, so just a simple zone file. This part is even, to me, more simple. So here, I've just created the zone file. So now I'm just defining this in my named.conf. rpz.local, type master. This is where my file lives. I'm not transferring in this case. Anybody, my zone, my server in this case can do the queries of this zone. Okay. So in a similar fashion, if I subscribe to a security feed for my response policy zones, I would have something like this. In this case, this is actually one of the free, and I should say kudos to Matt Stith from Spam House. These are actually, I stole these slides from him. So, with his permission, of course. But this is this is one of their free zones that they provide to anyone. So this is just a drop zone. So I am slaving drop.rpz.spamhouse.org from their name servers, and same thing. I'm not allowing anyone to transfer. Only queries from local hosts. All right. So I should mention that if you can't just like right now go configure your name server to do that. You actually have to contact Spamhaus. It's free, but they want to know, of course, who is zone transferring from them. Okay, so that will have to allow zone transfers to your authoritative server or resolver. And then to enable RPZ, this is essentially what you do in your global options. We define a response policy. In using the prior slides as our examples, zone rpz.local and zone drop.rpz.spamhouse.org. RNDC reconfig, and we're now, hopefully rewriting answers for malicious queries. Okay. So yeah, just some standard stuff. Anytime you make changes to this is beyond bind, beyond DNS. Anytime you make changes to your configuration, good idea to do a backup. Yeah. What we have typically seen people do is do pass-throughs for like 10 to 14 days. Watch the logging, watch the queries come in, and see which queries are actually going to have their responses rewritten. If you make sure you have your local zone listed first, because whatever, if I go back one slide to this, based on how I have listed here, I'm going to check my local file first. So if I have any whitelisting going on, you want that first in the list. Okay. Yeah. So one of the things I thought Rackspace did a good job of is notifying their customers ahead of time of what they were implementing and why. So if you do this, if you're an ISP, for example, and you want to do this on your resolvers, great idea to alert your customers that this change is coming. Twofold, if there's any problems, then they can let you know in a timely fashion. Okay. All right. So some of you may be thinking that, well, if I do some stuff like this, this is probably going to impact performance, right? I'm writing more logs. I'm actually looking at answers, and I'm rewriting based on these filters. So yes, there will be a performance impact. Okay. Now, a lot of that performance impact we've worked through and worked out based on people that have already deployed it. So when you deploy it, you can say thank you to people like Rackspace. Very good. If you have a really large environment, hundreds of thousands of customers and up, please, if you're going to do this with Bind, do use Bind 9.12. And whatever DNS software you're using, I would recommend you ask your DNS vendor. I'm thinking about doing RPZ or RPZ. What version do you want me on to do that? Okay. If you do Bind 9.9 or later, it will work. And for most cases, this is entirely appropriate. It won't knock your machines over, but again, if you're a very large deployment, use newer software. I mentioned that there are RPZ feeds. Here's a list of them. And if you get nothing else out of my talk, please go to dnsrpz.info. This is a site not run by us. It's run by some of the creators of RPZ and interested parties, but it's very agnostic on who you should use or why. Okay, so it's just a list of providers. Yeah, so you want to be on the lookout for false positives, of course, and that's just why the whitelisting is so important. You may know that the internet business is very tricky these days, right? So I can provide services that may appear legitimate to me, but to other parties, they may see that as malicious traffic, right? So what I'm saying is customers or organizations that you partner with may find themselves periodically put on these blacklist or response policy zones. So if you have a situation like that, you want to make sure that you whitelist, particularly your customer or partner organization IP space. All right. That's what I just said. There's a link to a KB article specifically on whitelisting if you're interested in that. Fast RPZ is something that, again, if you have a really, really large deployment, we encourage you to take a look at this. This is a new mechanism from Farsight. Note that it is not open source, so obviously you have to talk to the Farsight folks about that. We are not affiliated with Farsight in any way other than our founder, ISC's co-founder, works at Farsight. So. All right. Also note that Fast RPZ will work with other softwares like Unbound. All right, here's a list of references, and we have just a few minutes for questions if anybody has any. I think it's one of the security people that I said something about, so here we go.
It's actually not security related. Hi, I'm Ashley Jones, and I should disclose I'm from PCH. So a quick comment about the Quad 9 service. I think the statement about if you don't know why it's free, then you're probably the product is a bit unfair against Quad 9, which is nonprofit, and their mission statement is to provide secure DNS.
That is absolutely a valid point.
Yeah.
Totally acknowledged.
But the question I have is around, as a software engineer, so not a DNS operator or a network operator, how do you qualify or quantify this process being cheaper? And there was one other metric you put around there, because when you said an ISP would just hand out, Quad 9 or 8888, that is cheaper. So it comes at a cost of resources and hardware and whatnot. So.
Yeah, no, absolutely. So this is a conversation I have with lots and lots of people. So what I typically find is that if you have in-house expertise already, like heavy-duty Linux, Unix people, then to me it's cheaper to sort of go an open source route. If you don't have that, then it's absolutely cheaper to go the appliance route. So, yeah. Yep.
We have many questions.
Since the blacklist should update frequently, do
Yes.
you need to stop? Do you need to restart the DNS device to load new blacklist?
Okay, so very valid point, and actually, yeah, the feeds update really, really fast, and you do not have to reload. They come in over standard zone transfer. So when your provider does a change, they send a notify out to you, and that will initiate the zone transfer process. Yeah. So actually, in the Rackspace case study, that's where we had a lot of problems because updates were happening too fast and they were really large. So we had to do some tweaking to make that work better. Yeah, okay.
So this must be the last question because, yeah.
Well, there are no other candidates for that question. So, Tomas Gavrichenkov, Curator Labs. So you've mentioned Spam House. So I wanted just you to share maybe your experience. So how reliable is it? How much false positives are there with Spam House with different SBLs and different stuff available? So please share your experience.
Sure. So with the one I have the most experience with is Spam House because of this whole deployment we did with Rackspace and them. Where we had more trouble with them is that some of the partners ended up on this list. So it goes back to that gray area of is this malicious or not, right? There's some that are obvious, like this is a horrible thing, configure or whatever. But some people have differing opinions on what is internet abuse and what is not. So we had to work through some of that. So in terms of I've had good results in reliability from Spam House, and I have not had any reports of horrible false positive things from other providers.
I just wanted to share my experience this way. I had a case with Spam House when they actually blacklisted one of our IPv4 addresses, not IPv6 even once. Due to some malicious domain pointing to that IP address, but we had no contact to that. It wasn't. Oh, yeah. So it's overcaring, I guess, on the case of Spam House. So you can run into some problems with that, I guess.
Yeah. Thank you for that. Very valid point. So, all right.
Okay, given that,
All right.
thank you very much.
All right,
That
thank
was
you.
great. Yep. So next up, Gail from PCH. Okay, DNS content delivery Anycast network. Yep.
Hi everyone, welcome and thanks very much to the organizers for thinking that this is a nice presentation that should be presented here. My name is Gael and I'm going to be talking and giving a high-level overview of what it takes to build and operate a global content delivery network, and I've added the words Anycast and DNS because that's what we basically do at PCH. So this is the agenda of today. I'm going to go through a quick introduction of Anycast. I'll give an overview of our Anycast network, focusing a little bit on our footprint and how we got there. I'll put some stats on what it looks like a day of in PCH network. And I'll talk a little bit about how we plan our nodes and how we extend our network, and a bit more about operations and monitoring, so how we organize that. So first of all, saying that Packet House PCH is a non-profit. It's been working to support operations and security of critical internet infrastructure for a long while now. We're funded by government grants and service provisioning fees from internet operations, and we've got a global footprint, and I just wanted to mention this because our NOC is based here in Nepal, so I just wanted to mention that. It's a great it's great to have the NOC here and have some, be able to meet some of my colleagues here. So I just wanted to mention this and highlight this. So let's go into questions. So many of you probably know what Anycast is. Can I have a show of hands of who are relatively familiar? Okay, well, for the ones that do not, that will be a very quick intro, but I think it'll be useful. Anycast technology is a routing technology, and is used generally among content delivery networks, and it allows optimal routing to the closest of the locations. So you will build a cloud with distributed cluster of servers, which they're generally identical in terms of the data and the performance. And I say generally because we're going to see that you can size them according to what you expect the load to be in the different locations. Each of those instances will have a globally routable IP address. It will be used for management purposes, and that's where the Anycast comes in. It has an IP address that is shared among all of those instances, and that basically allows BGP to be able to route the query of the client towards the instance that is closest from a routing perspective to that particular instance of the server. So if we use a very simple diagram to show how this will work, we'll have this, a generic kind of network with a client, a number of routers, and we've put on the right-hand side, you have 3 instances of servers. You can imagine that the first one on the top is relatively close to you. There's only one router in between you, and or in this case 2, but 2 routers in between you and the server instance. On the middle one, there's a few more routers, and on the bottom one, there's 3. So the client will do a DNS lookup for, in this case, I put our Anycast address, ns pch.net, and it will only produce a single DNS answer. Despite having several instances of that same server and that same service, with that answer, you will give the work will be done basically by router 1. Router 1 will have to decide which way that query will go, and basically based on the routing table of router 1 has these 3 entries. These 3 entries correspond basically to all the 3 different instances. And while computing what the best path for that will be, well, he will determine that it will go into the shortest path. What's interesting about this is that although we know that there are 3 server instances, for the network and for the router is like if it was just one, but further away, for instance. So this is a little bit of the background or on how Anycast works and why it works very well to distribute the load among different instances. Now, Anycast has been used with DNS data for a long while. This is not something new. There were already some experiences back in '89, but the first time that it was discussed to actually have Anycasting authoritative root until the DNS was at one meeting in Montreal in 1995. As PCH, we began operating authoritative for CCTLDs and reverse address at 1997, and then we've been doing that since then. We first hosted an Anycast production of a root name server in 2002. For the ones that you don't know, we host in our infrastructure 2 letters of the root server, D and E, and around 400 top-level domains, and among them there's like about 100 CCTLDs. So that is, when I talk about DNS, that is the type of content that we're hosting in our network. And well, we operate services through IPv6 since 2000. That was the beginning, and since then, our network has, well, this is a view of the world that where you don't see some other countries where we're not present, but basically, is because of the whites. Apologies for that. This is an overview of the locations of our nodes. We have about 120 nodes. Among them, we have 14 to 18 global nodes or high-end installations around the world, in the United States, in Europe, in Africa, we have Johannesburg, and in the IPNIC region. From those nodes, in some locations, we connect to several exchange points. We work very closely with exchange point operators because exchange operators host these nodes within the premises as a service, as an added value service for the participants very often. From these locations, we have about 18 to 20. The numbers can be slightly off because the time that I prepared the presentation. And we are peering with 3,000 unique ASN peers and with all the 150 route servers that we can find. I've described the map includes different clusters of different size. So there will be small, medium, and large, and global and local nodes. And I'll be describing a little bit more of those later. So the only way of being able to expand and to extend our network in the way that we've been doing it is by following an expansion rate that is very close to the expansion rate of internet exchange points. Internet exchange points have been evolving over time, have been growing over time. There's around 480 approximately right now at the moment, and that's the only way that we've been able to keeping up with the growth of the internet. By some measurements, the internet keeps growing at a pace of, it duplicates every 13 months, so it is quite a high rhythm. And our expansion rate has also allowed us to be able to integrate more and more customers into our network. And on the right-hand side, you can see what is our footprint of the DNS secondary service. These are all the CCTLDs that we host in our infrastructure. So we've been iterating with our architecture, and this is a snapshot of what we're doing at the moment. We have a small, medium, and full cluster installations. The size of the installation depends on the location in which we're hosting and in which we're connecting, and it does make a lot of sense that small nodes will go into locations, generally small exchange points that might have a few, can be a few dozens megabit per second, a few hundreds up to 1-2 gigabytes, and then if we move, then we'll move into a middle installation. So depending on the demand on that particular location, which it's generally driven by the number of service providers and the number of participants there, we'll select the type of installation. We try to make sure that have redundancy, so we have redundancy at routing level with Cisco and Quagga. We have redundancy at OS level and name server. So we use bind and NSC in our clusters. We use virtualization. I will talk a little bit more about virtualization to have all our different services. And this is achieved thanks to long-term relationships with all the involved vendors. So I said I'll talk a little bit more about how does it look a day in PCH Anycast network, and as a I'm not really sure that I'm a manager, but I do like sometimes a bit of a stat. So this is how it would look the Anycast network. We're not the stats are only for our CCTLDs, basically because the monitoring system for the root servers and the root queries are in another host, so I couldn't compile everything at once. But you can basically see from that stats that the queries we're dealing with are coming basically from three main regions. Both ARIAN, RIPE, and APNIC take almost the entire other three regions where we serve most of our queries and we receive most of our queries. Now, why AFRINIC and LACNIC have so little? Well, this is related to several challenges, I would say, that is not that PCH faces those challenges, but somehow we do have installations, we do have clusters. Yeah, we do have clusters, we do have installations, but somehow the nature of the interconnection market in those countries and the nature that a lot of times large networks would not peer at domestic exchanges make that, for instance, in locations where we should be peering and exchanging traffic domestically in a country, we end up having to peer somewhere else. And that somewhere else is generally a large interconnection hub. So, for instance, if you take the LACNIC region, we're continuously expanding our footprint, but a lot of the networks, even if we can peer at a local exchange, at a domestic exchange, they will peer with us somewhere else. And that somewhere else typically has been Miami. We're trying to work harder with networks and with network operators to make them understand that this is a win-win scenario where we deliver traffic locally to them, but well, there's it takes time. It takes a lot of time and a lot of discussion. So that will be, for instance, one of the explanations. Another one is that, well, I'll cover them later. So if we're looking at the APNIC region, how does that look? Well, you can see that there's between 4 and 5 different nodes we're taking care of the region. So both Singapore, Tokyo, Jakarta, Sydney, and Seoul will take the large majority of all our queries. What about V4 and V6? Well, the snapshot, these stats are very recent. I think I did it. I think they're from Friday. So you can see that the situation at the moment is largely we're receiving V4 queries on maybe 90%. So 9 out of 10 queries we receive are over V4 and 1 is over V6. I don't have a historical, I cannot go back like maybe 10 years and see how it was, but I'm certainly sure that the percentage and the ratio has been growing over time, and we hopefully expect that to continue growing. As I said, we're completely V6 enabled since 2000. So, and this is another view of how we balance our load. We have 14 to 18 global nodes, and you can see here in the graph that those nodes are taking, well, they're making their work. That's what they're called global, and that's because they're able to take up to 80% of the load. Our goal, our long-term goal, is to continue increasing the gray area that you see, and to be able to capture and to answer more queries with the rest of our nodes. So In terms of planning Anycast node, we were talking before about Anycast being something that it's not new, something that has been done for a number of years, and it's a robust and well-proven technology. And for instance, by some measurements, in some countries, E-root and D-root seem to be the fastest letters. So that means that we're doing our job pretty okay, and that's showing that something works well. That's one way of showing it. What do we consider when we plan for new sites? Let's talk a little bit about that. Well, one of the first things we consider is any invitations from an IX operator. So whenever there's an IX operator, they're starting out, they're building the exchange, and they're thinking about hosting services which are good for the community, and services that will make the name resolution faster and lower latency for service providers. Well, sometimes out of these conferences, we engage into discussions and generally like, why don't you come? Why don't, we would be very happy to host you. So this is one of the ways in which, we can start a conversation with an IX operator. We would also look at traffic levels, number of participants, and the prefixes at each of the exchange. So at any given time where we have to take decisions about, how to expand and in which direction, we look very much into these metrics. And as part of some of the resources that we've developed and we have put on our website online for everyone to use, I'll give a very, very brief on the next slide on the IXP directory, which is a tool that we internally use to make these kind of decisions, and that you also could be using if you wanted to get a better decision making using some of these criteria. Another criteria we use and that we consider is that having our two main our two transit providers. So in the way that Anycast work, the announcements need to be consistent, and they need to be consistent. And for that reason, we use two transit providers, Entity and CenturyLink. So as you can imagine, whenever we're continuing expanding and some of the nodes might qualify to upgrade from a medium installation into a full global node, those will require to have transit providers at the exchange or at the premise. So that would also help us to decide which nodes can be upgraded. And lastly, we will also look into the relative location of neighboring nodes. We try to be present in every country. So at country level, we try to be present. We try to have at least one node there. Obviously, countries have different size, have different number of networks and different customers. So depending on the nodes that are on neighboring countries, we might decide to go for a second city on the same country, or to decide into a neighboring country to locate one of our first nodes. So that's a little bit of the considerations where we plan new sites. I was mentioning before that delivering content in some regions can be challenging, and in emerging economies we can find that the interconnection market is less developed. There are less options to have discussions and conversations with internet exchange points, data centers, and see whether we can install a new site there. There's also, in some regions, in some countries, we do not find neutral exchange points that would welcome the installation of these services, and that is somehow problematic, because the way in which we introduce these services to new countries is through the connection with exchange points. And well, as I mentioned before, large networks might prefer not peering at their domestic exchange, and that has an impact in the way we deliver our traffic, and that's something that we could see before on the stats. It's work in progress. It takes years of discussion at meetings with different people until you reach somebody that can understand the benefits of it. We still haven't found a formula to share with you on how to do this, but whenever we go, we try to promote the idea that peering is good, is something that helps deliver traffic directly, and this is something that we're trying to continue doing. So I mentioned quickly that we have a resource which is available for everyone. It's hosted at www.pch.net/ixpderm. Ashley, who did a question before, he's one of the architects of this. You can use the directory. Is a canonical directory of internet exchanges that were built. That some of them are defunct, but you can basically filter by country, by region, by the IXP name, and even to see, filter to see whether we are present in that exchange. As I said, we use it very much ourselves, and then you can order the table that you get the results by the number of participants, by the traffic exchanged, by peak and average, by the percentage of V6 and the prefixes. Again, that is a very good planning tool. It can give you an idea if you're deciding, where you're expanding, which are the locations where you could be expanding. So I encourage you to go and have a look at it. In terms of operations, we run all our services in separate virtual machines. We have dedicated virtual machines for the instances of the root servers we host, the TLDs, and monitoring services. We try to keep them separate. It gives us a great deal, a better deal of autonomy, and we can tweak the performance of those machines as we need. Depending on the type of deployment, so small, medium, and large, as I was mentioning before, and the type of node, where it's global or it's local, we BGP announce a partial or full set of service. So small sites can be anywhere in the world. You can see small locations, very small exchanges with a few participants and maybe a few megabits of traffic exchange. There will be small hardware installed there, and we will do only local only. So we will only be announcing our services to the service providers we are exchanging traffic with, and we're having BGP sessions with, and we will do a partial service announcement. So only a few of our services will be available. For medium sites, there will be medium to high volume locations. We will still do local only, so we will only present services through direct BGP sessions with the participants, and we'll do a partial service announcement. And for global full sites, there will be generally global nodes in high volume locations, and there we present all the services, and not only to the peers that we interconnect to, but also through our transit providers. So we will only get, not only we will get the requests from networks locally at that exchange, but also from our transit providers, and that's the reason why we call them global as such. So whenever we detect there's a potential failure on one of our DNS nodes, we will withdraw the announcement of DNS, on BGP, and that's the way in which the node will temporarily disappear from the routing table, and a node that will be nearby, a neighboring node, will take over that load. It doesn't necessarily mean that it will be a global node that will be taking over, but in some cases it might be a global node. That's a kind of a high level overview. In terms of monitoring, we do have and we do keep multiple layers of monitoring to proactively detect issues could lead into a degradation of the service. So we look at hardware layer, like CPU levels, temperature, RAM usage. We look at the interconnection layer, port traffic levels, routing layer, looking at AS path and prefix announcements, see if there's consistency, see if there's any potential prefix hijack or used by somebody else. Routing layer, and service layer. So just making sure that the services are running correctly, there's no spikes, or if there's spikes, understand why there's spikes. We use, as passive monitoring tools, we use open source tools. Due to the complexity of some of the very specific content that we work with custom plugins for DNS and Dnssec. But basically, we use Cacti, Nagios to monitor, and we do net flow monitoring analysis as we need. Some of the active monitoring will be using RIPE Atlas and the DNSMon service, and I know that there's ambassadors here. So for the ones that don't know, the RIPE Atlas service is a brilliant service to monitor global performance. So this is something that we actively very much use. And I'm almost there. So the last slide was to discuss a little bit of some of the things that keep us busy on our toes. UDP spoofing and network operators now implementing BCP38 is something that still keep us busy and keep our NOC alert. We find, but because of the way that we run these very large Anycast network, when network operators do too much traffic engineering, it might become a bit harmful because of the way that we announce our roads. That's something that our NOC is very much aware of, and we work very much with every time there's need to patch, there's a new zero-day exploit affecting name servers. There's a great deal of work behind to make sure that all the software is up to date. We're trying to automate a little bit more the provisioning process to reduce the time that it takes us to deploy new nodes with a combination of tools. And we do a little bit of research lab work to see into benchmark new or other alternatives and see how well they perform in our environment. For instance, I'm giving an example of not DNS. That's one of our senior engineers who gave me that. Okay, so that's it. Do you have any questions?
Any questions? Okay, let's take just one question because we are a bit behind of the schedule.
Hello, Alexander Azimov, Kyoto Labs. Why are you still using Quagga?
We use Quagga in our route collectors. So in each of the locations that you see, we run not only AS42 for our DNS production, but we also run route collectors that are listening to all the BGP activity, and we collect that information and we publish that. And the way in which we've traditionally been using it is through Quagga. It's a versatile and an easy way for us to keep that. But the production routers are they're all Cisco routers. So Quagga is what we use for our route collectors. Yeah. It's only.
Okay, then thank you very much.
Thank you very much.
That was good. So next up, Artyom? Yeah, Artyom. he will talk about DNS survival guide.
Yeah.
Give me a sec.
Yes, of course. Fine. Yep.
So, hi everyone. Yeah, we are a little bit behind the schedule, but we'll try to do it fast. First of all, a disclaimer. What we are mainly going to talk about is maintaining a DNS zone on an authoritative server of an enterprise. Recursive DNS servers are some kind of out of scope of our discussion, yet some points made are also valid and they apply to recursive servers as well. But main focus is authoritative servers. So let's start. Let's start with a bit of history. At the beginning, at the time of dinosaurs, which is like 80s, humanity was struggling for a solution to a civilization-threatening problem, which is name resolution. On a contemporary computer, you can still spot an artifact from the distant past. Oh, okay, yeah, good. An artifact from a distant past called a host file. A host file is essentially a clear text file, which is a line-by-line mapping from an IP address towards what's supposed to be a handful of host names. So if you wanted to resolve a host name in 80s, you can just open this file, read it through, find out the host name you're looking for, and find out an IPv4 address it's referring to. But the issue was that if your internet consists of a large number of computers, and I mean really large, like 1,000, you easily run into all sorts of troubles maintaining and distributing all those files with your infrastructure in case a new network service is fired up. So, thus a network protocol was born called Domain Name System Protocol, with network clients and servers, but the whole purpose of this new protocol was again simple and very alike to this intentionally wrong pseudocode in C. So it was just simply taking a string of ASCII characters and converting that into a 4-byte integer, which is an IPv4 address. Yes, some other functionality was also built into the protocol, but it was mostly, again, with few exceptions, a service stuff required for the protocol itself to run, and the main purpose was still something like that. However, this was in the middle of 80s, and the time kept changing. So, roughly about 10 years ago, World Wide Web was invented, and enterprises started to conquer it. World Wide Web imposed new requirements for DNS protocol and kept doing that. New applications like load balancing, geo-balancing appeared, and then started being replaced with policy-based optimizations we'll discuss later. Next, large enterprises wanted business continuity and redundancy, so they have opted for DNS failover mechanisms. More and more functionality was added via extension mechanisms like Dnssec, like client subnet, and more. Next, IPv6 appeared, and also different security mechanisms were added to DNS protocol. Currently, there's such a lot of features, so that at that point, even if you are not using them, you'll definitely start at some point, or else your competitors will do. And here's our problem. Given the way DNS evolved, given all this inherent complexity, how should an enterprise maintain its DNS infrastructure? So there are basically two main options. Either you can run it yourself, or you can outsource it. And with each approach, there are more questions to it. Do you use to serve your DNS responses, right? Because you need some kind of software server product for that. And in case you are going with outsource, then how do you choose a management service provider? So this is our problem statement. Let's figure out, starting with option 1. So how do I choose a software product at the point where the overall requirements are not still very clear, and business might want at some point something more from us? So a naive approach would be A. The server software should be scalable in order to handle all the load the marketing department can bring into you. B, it should be feature-rich in order to handle our future suggestions and requirements. So let's start with scalability. So here, like about 5 years ago, we've carried out a complex benchmarking for different DNS software releases. There was a comprehensive list of software products, which is on the slide, to test. And we've brought some hardware, quite powerful at that time, for that. So our purpose was purely academic. So we wanted just to find out who runs better code base with hash tables and stuff. So for this is why we've mixed authoritative service with caching resolvers. And for the authoritative thing, we've generated somehow 300 of zones. And for caching resolvers, we've kept pretty much the same amount of data in a warm cache. So we've done our benchmarks, we've got our results, we've shared them with community. I'm referring to our previous presentation, which is a link on the slide. And the slides will be available after the talk on the Apricot website. So we've shared the details, and when we did that, the question everyone kept asking us was, guys, where's bind? So, frankly speaking, during preliminary testing, bind appeared to show results so disappointing, in some cases completely indistinguishable from the XX, that we've decided to skip benchmarking bind at all. However, 4 years later, when we've decided to repeat our benchmarks just to see if anything has changed, we've added bind to that. So here on the slide is the amount of responses. So as more and more queries kept coming in, up to a figure of 2 million by 3 different servers under 3 different conditions. The higher the graph is on the right side, the better the results. Ladies and gentlemen, here is bind. Regardless of affinity and other configuration options, bind has failed to catch up pretty soon. At the stage there were about So, note that this time the scale has changed somewhat. On the y-axis, there's now not the exact amount of responses served, but the percentage of successful answers. So the closer to 100% on the right side of the slide, the better. Here, at a rate of 1 million queries per second on a server dedicated for this very task, if there are no security advisories published for a software product, it doesn't necessarily mean authors are good at writing software, because it might as well mean they are bad at writing advisories. And again, what features are on the product's roadmap? How quick will new features be implemented into server software? So here, with all sorts of those issues, we always tend to get back to our requirements. Maybe they are just excessive, no? What is this feature set we might want? Is it really big? And how really scalable a good old DNS server should be? Because at its core, a DNS lookup is a simple thing. Yeah, here is the Facebook page of APNIC. And I've hard reloaded it quite a few times and collected traffic dumps. So here we are. And like back in the time of dinosaurs, you could easily expect like 2 to 10 DNS packets in the dump. But today we have all sorts of subdomains, CDNs, counters. So an average Facebook page makes about 50 DNS queries, which accounts for 100 of packets here. It's still, when you are just counting, it's still 1/8 the amount the HTTPS service. When you are talking about the type conversion thing we've started with. In theory, there's no difference between theory and practice, but in practice there is. What if we want more? Let's start with geobalancing. The other in, say, California. You might want your customer from South Korea to go towards your server location in Japan, because California is too far away. Sadly, there's no country data present in an IP packet, so you should use a proprietary database from some vendor here to map an IP address to geolocation. So, the problem is that reliability of such databases for that particular task is questionable, to say the least. Here is a simple example. I've took the demo of one vendor's website and submitted Google public DNS IPv4 address. Here is what's returned: United States. Sorry guys, but 4 8s are anycasted, as Gail has pointed out. They aren't in United States or in Europe or in Singapore. They are in each of those locations. And another funny thing here, by the way, is that the database not only returns us the country, but also it gives us GPS coordinates. Where's that? Let's have a look. Whoa, in the middle of Cheney Reservoir. How's the water, gentlemen? An Anycast server went underwater, and still no arrests. How come, GeoIP database? Well, frankly speaking, this is just wrong, because Google Public DNS isn't in the United States. Actually, there's even more to it. Any geodatabase out there has a dilemma of whether to return a location of the owner or the maintainer of an IP address, or an actual location from which the BGP announcement of an IP prefix is made. GP databases are generally, to say, unreliable for anything except raw statistics. There's a long story about those GPS coordinates, by the way. Please follow the last link on that slide. But the overall idea is the database does know the results returned are inaccurate, sometimes intentionally inaccurate. Yet the database API doesn't give us a clue to that. No warning, no error. This is just one of the long list of issues. I'm not blaming MaxMind here. By the way, those databases are all the same. I've tried a lot. For instance, vendors are used to import data from regional internet registries databases where the information is often inaccurate and outdated. But probably the main issue with geo-balancing is that if you have a server in Japan and a customer in South Korea, the traffic between them doesn't necessarily go through the Pacific Ocean. It could as well go all the way through Atlantic due to ISP policies and routing policies of network operators. As I've said before, there's no country data in an IP packet, and there's no geography on the internet. There's just network topology, and there are no countries, just autonomous systems and their mutual relations. So with this in mind, some DNS operators recently started offering more granular approach to balancing. Here, for example, is NS1's NetFence filters, which can be used to subsequently refine answer policies for different autonomous systems numbers and prefixes. So in case your South Korean users start complaining about increased latency, which might be the case today because there's Olympic Games there and a lot of your customers are probably there, you can simply add specific DNS policies for problematic Korean prefixes, like target them to California server, which is closer in terms of network policies, and problem solved, management is happy. So, geo-balancing and prefix targeting may be extremely useful for some enterprises. The issue with that, however, is that it, of course, adds greatly to the computational complexity of a simple DNS response. Next on stage, dynamic configuration. This is about how you deploy changes in DNS configuration. Here's an example of how it was done in Spotify like 5 years ago. There was some chat in an internal messenger flooded with off-topic, as a matter of fact. And from time to time, you have an engineer in duty shouting in this chat something like, DNS deploy! This meant that he is now going to deploy changes in their DNS setup. This desperate shout itself served two purposes. First, everyone around got notified that some configuration changes are ongoing, so in case something goes wrong, they know where to seek revenge. Second, it served as a mutual exclusion, a locking mechanism. Of course, this approach allowed for all sorts of troubles. Spotify guys are brilliant. They are not doing this anymore, and neither should you. Because today, DNS isn't a static configuration file anymore. This is an API for configuration management systems and applications. Service provisioning, monitoring, and statistics and policy management, all these are tasks for this API. An enterprise will want this sooner or later, and working with DNS like old style, with manual deployments and manual reloads, and human errors isn't a contemporary way to do that. So, next on stage, failover. So the task is simple. If you have like 2 servers in your DNS record for redundancy and one of them goes down, you want it to be taken out of DNS rotation as well. For this, you need some sort of monitoring tool which will discover that one of your servers is unavailable and then report to a DNS API we've discussed before. DNS-based failover has its issues. There's a graph of, for example, HTTPS requests towards a server, which HTTPS server, yeah, which was taken out of DNS rotation about quarter after 10 p.m. So on the left side of the slide. The TTL of the DNS record was 120 seconds. As you can see, 15 minutes ago, 1/3 of traffic was still flowing towards the server, which was at that point expected to be down for a while. Only roughly an hour ago, the traffic finally stopped flowing. The square below the blue line here is the amount of customers that would have been lost for a website in case of a real emergency. This is due to, as we guess, some policies in some recursive resolvers on the side of local ISPs. This issue doesn't reproduce stable, but it happens from time to time. It appears like reducing TTL to, say, 20 seconds helps to fix that. But this way, your DNS traffic will be easily 6 times it was before the change. Next to the security, as we've discussed before, you need to figure out how the author of your DNS software handles all the vulnerabilities. And another issue, security issue, is DDoS. So first, DNS is UDP-based in its core, so it's more exposed to volumetric attacks, like amplification attacks and so on. So you need to use effective line rate challenges or handshakes, which are built somewhat into DNS protocol to verify the IP sources of inbound traffic, not to handle all the UDP packets coming from a spoofed source in your user space. For high-level attacks like water torture, you probably need some packet analysis, request analysis, statistics, and blacklists to filter the traffic. And again, IP blacklists are useless without those line rate challenges, as DNS traffic can easily be spoofed. So with all other security stuff, yeah, and by the way, not to forget about it, to handle large attacks, today towards DNS server, you need an Anycast network, because for DNS, it's not an option or suggestion today. It's a must, because DNS attacks are very cheap for an attacker, but extremely disastrous. So there are also other things like Dnssec. There are almost 200 RFCs related to DNS, not even counting working group drafts. So now, homegrown DNS starts to look pretty much rocket science. Now, what's about service providers? Because there are plenty of them, I've outlined a few on this slide. Sorry for not putting your favorite managed service provider on the list. I have only a slide of this size. So, issue remains, how do we choose this way a managed DNS service provider? A good news is, probably you don't need to choose. Introducing SRTT, a smooth round-trip time. This is a mechanism which is, by the way, already deployed in most small office, home office, and enterprise networks, mostly accidentally, by the way. An S1 study suggests that though only 50% of resolvers present on the internet have it, those 50% of resolvers actually account for up to 90% of internet traffic. SRTT is intended to help you running a lot of authoritative name service simultaneously for a zone, benefiting from the combined coverage of all of them. It works this way. If there are, say, 2 name servers for a zone, SRTT-enabled resolver will query both and then use the one which responds faster in order to reduce latency for a DNS client. Here is an interesting example of how it works. But first, who is familiar with a box plot? Please raise your hands. Okay, so meet box plot. A box plot is a method for graphically depicting groups of numerical data. In our case, that would be response times of DNS queries through their quartiles. So the bottom and the top of the box are always the first and the third quartiles, and the band inside the box is the second quartile, which is essentially a median. The ends of the whiskers are always the minimum and the maximum of all the data, or something close to that. So, when we're speaking about the response times, the lower the box plot is on the graph, the better. So here are Stack Overflow's DNS measurements in New Zealand. Stack Overflow at that point operated 2 DNS operators, Amazon Route 53 and Google DNS. Apparently, Route 53 at that point had a point of presence somewhere close to New Zealand, while Google hadn't. So if you say, Route 53 is on the left side, and Google DNS is on the right side, so the box plot is higher. So as you can see, the latency is bigger. So if, say, you replace Route 53 with Google, you'll easily get complaints from your New Zealand users due to heavily increased latency. However, what if you don't replace, but add Google in line with Route 53? Will there be any drawbacks for the DNS performance? Here is the result in green. As you can see, a combined solution performs much better than Google. It's roughly equal to Route 53, so adding even a heavily underperforming DNS operator doesn't affect latency in a bad way. A funny thing, by the way, here, and what's even more funny, is that the combined setup, despite Google's inefficiency in New Zealand, performs even better than Route 53 alone. The box plot is even lower. This is probably because there's a couple of locations in New Zealand where Route 53 performs really bad, probably due to routing policies we've discussed before. And in those locations, due to SRTT, Google takes over. So if you run 2 solutions simultaneously, you benefit from both solutions in the most marvelous way. So here's how you can choose a DNS provider. Just pick a few, the more you have, the better. In my belief, up to 4 or 6 will be fine. This way, in case, by the way, you are paying them for the real traffic usage, it's easy to replace the underperforming ones, because those underperforming are those who will handle the less traffic because of SRTT. So those underperforming are those whom you are paying less. Having multiple providers also helps with operational issues and failures and maintenance windows on behalf of your providers, or them being DDoSed or anything else. There's a mechanism built into DNS for distributing zones, that's zone transfer, but it's, to say the least, not feature-rich. So you'd better stick to providers with nice and convenient API. So if you are an ISP, make sure that SRTT works on your network for your customers at your resolvers. And if you are an enterprise or some company of some sort, so I hope that now you'll be able to build your DNS solutions in quite a better way. That's it. Sorry for breaking our schedule. Questions?
Any questions or comment? Good? Yep.
When you
Yeah.
your first slide that Bime wasn't on, I was going to say thank you for not putting this up there, but then you had another slide. So anyway,
Okay.
we're obviously aware of that. What I guess my question though is, do you have a final recommendation? In terms of, do you outsource? It sort of goes back to the question earlier. Do you outsource or do you do in-house? What is your recommendation to folks?
It will take another hour to discuss that, but because there are different enterprises with different requirements, my idea is to outline what each and every solution out there has its advantages and disadvantages. Here are they enumerated. So you might just want to find out what's more important for you, and then you can choose either way. So the last point, that if in case you'll have any questions, You can find me down there at, I'll be there till the end of Apricot. I'm wearing this distinctive ready hoodie. So feel free to find me and ask me questions. So thank you very much.
Thank you very much. So now we are going to the lunch break. And then please do not forget about picking up your T-shirt from the registration desk. So see you in this afternoon.